All right, welcome to The Explainer. Today, we're diving into what is arguably the most powerful, elegant, and honestly indispensable map in all of astrophysics, the Hertzsprung-Russell diagram. If you want to understand the universe, how long stars live, what they're actually made of, and where they're heading, you absolutely have to understand this map. It is the ultimate tool for decoding the cosmos. So, here's our roadmap for today. We're going to decode the cosmic map itself, run through the stellar alphabet, and figure out where specific stars actually live. Then we'll trace their lifespans, look at how this applies to the real-world physics of star clusters, and wrap up with how we're upgrading this map today. All right, part 1, decoding the cosmic map. Let's look at the history and the axes. You know, the story behind this diagram is a fantastic example of simultaneous discovery. It really starts back in the 1800s. The foundational work was brilliantly laid out by the Harvard computers. These were pioneering women like Williamina Fleming, Antonia Mori, and Annie Jump Cannon. They meticulously classified tens of thousands of stellar spectra completely by eye. It's wild to think about. Then, building on that massive catalog, Ejnar Hertzsprung in 1911 and Henry Norris Russell in 1913 both independently realized something huge. They saw that stars didn't just scatter randomly out there. No, they clustered together based on very specific physical traits.
Now, what's really fascinating about how this is set up is how it pits a star's true intrinsic brightness right against its surface temperature. On the vertical axis, you've got luminosity. Think of that as basically how much energy the star is pumping out every single second, measured against our own sun's luminosity. And then, on the horizontal axis, we plot the star's surface temperature, or its spectral type. And that actually corresponds perfectly to its visible color.
But wait, I gotta call out a kind of counterintuitive quirk here. The horizontal axis, it actually reads backwards. Yeah, temperature decreases as you move from left to right. That means the blazing hot blue-white stars are anchored way over on the left side, and the much cooler red stars are sitting over on the right. It takes a second to get used to, but once you wrap your head around that reversed axis, reading this whole thing just becomes second nature. Moving right along to part 2, the stellar alphabet. Let's talk OBFGKM and luminosity. So, to sort stars along that temperature axis we just talked about, astronomers use a highly memorable mnemonic. Maybe you've heard it. OB, a fine girl or guy, kiss me. This little phrase anchors the entire complex stellar alphabet, running from the blazing hot O class all the way down to the dim, cool M class. And it doesn't stop there. Each letter is broken down further into subclasses from 0 to 9. We've even got extended classes for peculiar stars, plus L, T, and Y for these ultra-cool brown dwarfs. Get this, some of those have methane and ammonia in their atmospheres and are literally barely warmer than a household oven. Crazy, right? So you're probably wondering, exactly where does our own yellow sun fit into this whole stellar alphabet? Well, it sits right there in the G class. The sun is a G2V star, which basically means it's a yellow main sequence star with a surface temperature of roughly 5,800 Kelvin. Now compare that with an O-type star, which is just roaring at over 30,000 Kelvin, or on the flip side, a cool red M-type star like Proxima Centauri. Okay, part 3, mapping cosmic neighborhoods. Let's see where these stars actually live. By far, the most populated district in this cosmic city is the main sequence. It's this prominent diagonal band stretching from the hot, bright upper left down to the cool, faint bottom right. Honestly, stars spend about 90% of their entire lives right here. It's their stable home. While they're here, they exist in what's called hydrostatic equilibrium, just peacefully fusing hydrogen into helium. The inward crush of gravity is perfectly, beautifully balanced by the outward push of nuclear fusion. But what about outside the main sequence? Well, that's where we find the extremes. Up in the top right region, you've got the supergiants. These things are massive and brilliantly luminous, but surprisingly, they actually have cool surface temperatures. So for them to pump out that much light, they literally have to be physically gigantic. Then, completely opposite to that, in the bottom left region, we have the white dwarfs. These are tiny, extremely faint, but incredibly hot. Basically, they're the super dense, burned out remnant cores of stars that have already shed their outer layers. Which brings us to part 4, the life cycle of stars. Let's trace those stellar evolution tracks. When it comes to stars, mass is destiny. It completely dictates a star's ultimate fate and how it's going to move across this map over time. High mass stars, they totally live by the motto, live fast, die young. They blaze intensely, burn through all their hydrogen in just a few million years, and then collapse catastrophically into supernovae. But on the other extreme, you have low-mass red dwarfs. These guys are the marathon runners of the cosmos. They burn their fuel so slowly, so frugally, that they can last for trillions of years. I mean, they'll far outlast the current age of the universe itself. Let's actually trace the specific step-by-step track that a sun-like star is going to take. It starts its life out comfortably on the main sequence, just happily fusing hydrogen. But when that fuel finally runs out, its core contracts while its outer layers swell up, and that moves it up and to the right onto the red giant branch. Next, it undergoes this sudden, explosive core ignition called a helium flash, which drops it down onto the horizontal branch. Eventually, it swells right back up again on the asymptotic giant branch, before finally shedding its outer layers entirely. After that, it plummets all the way down to the bottom left, ending its days as a glowing hot white dwarf cinder. All right, part 5, physics and star clusters. Basically the so what application of all this. Here is where this whole concept becomes an incredibly practical, honestly mind-blowing tool. If astronomers look at ancient globular clusters and find what's called the turn-off point, which is the exact spot where stars are exhausting their fuel and veering off the main sequence, they can actually date the entire cluster. Since more massive stars hit that turn-off point earlier, using this technique proves that the oldest clusters, and therefore the universe itself, is roughly 13.8 billion years old. Think about that. This one diagram literally gives us the age of the cosmos. The math backing this map also neatly visualizes some incredibly profound physics thresholds. Take the Chandrasekhar limit, for example. This is an exact mass threshold of roughly 1.4 solar masses. If a white dwarf accretes enough matter from a companion star to tip over that exact limit, the quantum forces that are pushing back, something called electron degeneracy pressure, they just fail. Gravity wins. The star collapses and triggers an absolutely massive Type A supernova explosion. And its uses go way beyond that, from measuring cosmic distances using something called spectroscopic parallax, to mapping out the complex chemical structure of our own Milky Way. The HR diagram is absolutely the workhorse of modern astrophysics. It is even critical for characterizing the host stars of newly discovered exoplanets. Because, well, you can't really understand a planet without understanding its sun, right? Oh, and it's also used for astroseismology. That's literally measuring the internal heartbeats and oscillations of stars to pinpoint their exact locations on the map. Finally, part 6, modernizing the stellar map. We're talking Gaia and 3D models. Right now, the European Space Agency's Gaia mission is delivering sub-micro arcsecond precision, completely transforming astrophysics as we know it. It's revealing these incredible fine structures, like the actual physical split between hydrogen-dominated and helium-dominated white dwarfs. It's also uncovering thousands of faint, ultra-cool brown dwarfs that we simply could not see before. And, theoretically, we are even moving beyond just 2 axes. New 3D stellar models are pushing the boundaries by adding dimensions for stellar rotation and chemical composition. It's making our understanding so much more robust. There's this great quote: "The HR diagram encodes nuclear physics, gravitational physics, quantum mechanics, and fluid dynamics into a single, comprehensible visual form." I mean, that perfectly captures why this single tool remains the undisputed crown jewel of stellar astrophysics. Everything from the quantum mechanics keeping a white dwarf from collapsing to the complex fluid dynamics of a swelling red giant, it is all beautifully synthesized right here. So as the Gaia mission continues to map billions of stars with unprecedented precision, we have to ask ourselves, what new cosmic secrets is this diagram going to reveal next? As we peer deeper into the galaxy than ever before, this century-old map isn't just history. It is the absolute key to our future understanding of the stars. I really hope this explainer helped you master the ultimate map of the cosmos. Keep your eyes on the sky and always stay curious.